Hello, everybody. Thank you all so much for joining us this afternoon. Today, we are convening to highlight the incredibly important work that's happening out of the Office of Science at the Department of Energy and how that work is tackling the climate crisis. So I'm going to brag a little bit here because the Office of Science is America's single largest source of support for basic research in the physical sciences, the single largest support. So every single day, they're getting us closer to breakthroughs that can change our tomorrow, really. And as we make our way through yet another summer of droughts and heat waves and wildfires in the West, the Office of Science's efforts to study climate change could not be more important. We play critical roles in both observing current climate-related developments and in then predicting where they're headed. Because we're using this talent in our national labs and in many of our universities, it allows our Office of Science to collect data that shows us what's happening in our atmosphere and our ecosystems right now, which is data that shows us where the future is going to lead. And of course, how we can work on strategies to raise resilience and make sure our communities are prepared. We won't know how to fix the problems or address them unless we know what's underlying them. And so right now, our biological and environmental research team at the Office of Science is researching the impacts of droughts and wildfires. They're measuring how atmospheric patterns are affected by carbon emissions. They're projecting the impacts that we're going to experience in the years ahead as these emissions grow or shrink or plateau. And thanks, to some of the most sophisticated tools on the planet, they're able to do this. So our atmospheric radiation measurement facility, that means ARM, A-R-M, Atmospheric Radiation Measurement Facility, it boasts an unparalleled ability to observe interactions between changes in our atmosphere and changes in our climate. And then our Environmental Molecular Sciences Lab is home to some of the world's best analytical capabilities, which allows our researchers to make predictions around changes within various ecosystems at the atomic level. And then DOE owns the world's fastest computers in support of science. And the good news is these capabilities all have allowed us to create the world's first high-resolution climate model. And it gave DOE a role in the largest Arctic expedition in the history of science. We used the ARM facility, the ARM facility, to collect one-of-a-kind atmospheric measurements. But the bad news is that this work has really confirmed some deeply alarming truths, which is, of course, that the climate crisis is here and it's only going to get worse the longer that we wait to act. All of us in the Biden administration recognize the urgency of this moment, and it's why the president has set very ambitious goals to put the country on the path to truly tackling the climate crisis. We're doing everything we can to cut emissions in half by the end of the decade, and then to reach 100% clean electricity by 2035, and then to achieve net zero carbon emissions by 2050. And that, part of that is giving the Office of Science and our national labs full support to conduct their research and then to use their data to shape our response to climate change. So earlier today, we announced awards that totaled $11 million for 17 projects that are focused on improving the accuracy of climate modeling around flooding and drought and heat waves. And that follows $15.6 million in funding that we awarded earlier in the month for atmospheric research to boost our climate modeling efforts. And then in just the next few weeks, we're going to have another funding announcement for Earth and Environmental Systems funding. So these efforts are going to continue throughout this administration's terms because we believe scientific inquiry is the key to understanding the world around us, and it is our guide to overcoming the challenges that are facing us. President Biden affirmed that support for science with a memorandum that he signed in his first week in office. He's directed every single agency to make evidence-based decisions that rely on the best available science and data. And a few months later, he tapped one of DOE's own, Mike Kuperberg, to once again lead the US Global Change Research Program. We'll quadruple down on science once we pass the Build Back Better agenda into law, which is going to invest billions of dollars in our national labs and in our country's overall research capacity. And we're going to continue our unique efforts to observe and to model and to predict the impacts of climate change, particularly for the energy sector. And we'll ensure that our findings help to guide partners that are engaged in climate action throughout the administration. And that includes the White House Office of Science and Technology Policy, and our special guest for today, Dr. Jane Lubchenco. Dr. Lubchenco brings decades of leadership in scientific research to the table, including a stint heading the National Oceanic and Atmospheric Administration, or NOAA. Today, she serves as the first ever lead for climate and environmental science efforts in the White House. And she plays a huge role in the administration's all-star team for climate action. I'm so thrilled that she's joining us today for this virtual roundtable discussion. Ladies and gentlemen, please welcome Dr. Jane Lubchenco.
Thank you so much, Secretary Granholm. I really appreciate that warm welcome. And I share your excitement about today's announcement. This is really, really thrilling. What a treat it is to be part of an administration that is moving so aggressively to tackle the climate crisis. These stripes behind me tell a sobering tale. This graphic represents the change in temperature for the whole Earth from the cooler colors beginning in 1850 all the way through to the red hot colors you see representing 2020. But as dramatic as this image is, it doesn't begin to tell the human story behind the wildfires, the smoke, the drought, the heat waves, the flooding, sea level rise that Americans are experiencing every day. Nor do these stripes convey the great economic benefits and amazing good job opportunities that come with smart action to tackle climate change. So our response to the climate crisis will be most effective if it's grounded in strong, comprehensive scientific understanding, which is exactly why today's announcement is so very exciting. We have already benefited, as the Secretary has noted, from DOE's long history of advancing climate knowledge and solutions, from carbon cycling to cloud physics to CI, will accelerate progress in understanding atmospheric and ecological processes, and that will lead to improved Earth system models and therefore more precise and higher resolution projections of the future. So DOE has played a pivotal role in creating the knowledge that we depend upon today. And the investments that the Secretary is announcing today and in the near future will help ensure that we're able to meet tomorrow's challenges as well. I want to take this opportunity to recognize the second critical role that DOE's Office of Science plays, and that is as a leader in the 13-agency partnership, the U.S. Global Change Research Program, or GCRP. In my role as Deputy Director for Climate and Environment at OSTP, I work closely with GCRP, and I have challenged this stellar group to expand their repertoire and enhance their ambition. This nation needs even more useful and usable knowledge if we are to succeed in mitigating and adapting to climate change. I'll let you in on a little secret. I look to DOE as a trusted partner and leader in US GCRP to rise to this challenge and help US GCRP be as smart, strategic, and useful as possible. The US GCRP is also developing a new decadal strategic plan and our 5th national climate assessment. We have strong public engagement plans for both of these activities. And so I encourage anyone who is interested, to watch for engagement opportunities, or to visit the USGCRP website to learn more. For those of you with experience and expertise to share, consider reaching out directly to USGCRP to volunteer to serve as an author or even a review editor. So in closing, on behalf of the President's Science Advisor, Eric Lander, and the White House Office of Science and Technology Policy, I offer our deep thanks to our partners at DOE and to Secretary Granholm for continuing to support the nation's science needs. Thank you.
All right. Thank you, Dr. Lubchenco. It is so great to be able to call you a colleague in this administration and a partner. So now it's my pleasure to introduce these three brilliant, talented women from three of our national labs who've graciously joined us for our roundtable discussion. Margaret Torn. Margaret is a senior scientist and a project leader at the Lawrence Berkeley National Lab, and she leads research on ecology and the carbon cycle to help us understand causes and impacts of climate change. And Nikki Hickman of Argonne National Lab is the Associate Director of DOE's Multi-Laboratory Atmospheric Radiation Measurement User Facility, which I talked about earlier, which provides data to thousands of users worldwide to improve climate prediction models. And Kate Calvin is a project leader and climate economist at the Pacific Northwest National Lab, PNNL, Joint Global Change Research Institute, where she studies integrated assessment modeling that offers projections around impacts on people and communities. So Margaret and Nikki and Kate, thank you so much for being here. Let's jump right in if we can. So many of our viewers today may be wondering, maybe they're not, maybe they know this is true, if these wildfires and droughts and hurricanes and winter storms that we keep experiencing each year are intensifying. And if that sounds like you, well, it's true. The data shows you're not wrong. Ecosystems across the planet, as we are seeing, are becoming more and more vulnerable to climate change, especially in drought-prone areas like the American West. So Margaret, you've got over 20 years experience conducting field experiments on vulnerable ecosystems. I'm wondering what you see as the biggest climate ecology challenge on the horizon, and how can DOE help to address it?
All right, thank you. And it's so nice to be here with all of you. So you're absolutely right. Ecosystems are facing more frequent and more severe disturbance now. And so I think the grand challenge we face in ecology and climate is that at the same time that our natural and working lands are facing or experiencing more extreme weather and wildfire, we're also counting on ecosystems more than ever, not just for food and water for human needs, but now also to help us protect the climate by sequestering carbon and providing sustainable energy. So we need our scientific research to better understand the threats, but also to create solutions, such as how to make our landscapes more resilient and protect vulnerable communities, and how to protect the biological diversity that makes all these benefits possible. In my work, I'm focusing on the world underfoot and the world overhead, as I say, the soil and the atmosphere. And soils contain a lot of organic material, which means they contain a lot of carbon. So we're conducting field experiments where we artificially warm the soil. We're warming forest soil and grassland soil to simulate the future and quantify how the world soils will respond to a warmer climate. And what we see is that warming stimulates decomposition by microbes, and those soils release more CO2, which, as you know, is a greenhouse gas. But on the solution side, our studies are showing us how to increase soil carbon storage to remove CO2 from the atmosphere with good management. In terms of the atmosphere, one of the big questions is how to measure the impact of ecosystems on the climate. DOE supports the Ameriflux network, which connects several hundred scientists at sites from Point Barrow, Alaska to the southern tip of Chile, who are all measuring the flow of CO2 and water and energy between land and atmosphere. So we're providing data to thousands of more people around the world, and they're using these observations to better predict future climate, but as well to enhance the productivity of cropland and forests. I think DOE research and research by other agencies as well has provided a good foundation for solving problems. So I want to mention that as well. There are many areas in which we already know enough to act. I mean, we know that trees in urban areas, for example, schoolyards, can help cool summer heat waves. We know that it's easier to protect soil health than to rebuild a soil, which is critical for farms and grazing land. And we know that these things can be done in a way that protect the most vulnerable, the rural and urban populations. But the rapid change we're experiencing now calls for more active stewardship to protect biodiversity and increase resilience of natural areas. And with the rapid warming and change in extremes, we can't simply use the past to predict the future. So that's why this is such an important research challenge. And I think this frontier for climate and ecology research is better understanding those vulnerabilities and creating solutions together at the same time.
Thank you for that. I think Dr. Lubchenco has a question.
I do indeed. This question is for Nikki. So Nikki, for the last decade of your career, the most recent decade, you focused on developing new tools and methods for observing what's happening in our atmosphere. And these innovations that you've worked on have really helped us significantly improve our climate models. So could you tell us a little bit about how the ARM user facility that the Secretary has referred to helps us combine observations, models, and AI to more rapidly enhance climate predictions?
Sure, I'm happy to. So ARM is a Department of Energy user facility, which means we operate observatories that take measurements that are critical to the science community's needs. So in Earth system predictability, you can imagine this takes us to some very challenging locations in the world. We've operated in Antarctica, the tropics, the mid-latitudes, the Arctic, and as mentioned earlier, on an icebreaker that was frozen into the ice and for about a year floated along and even crossed the North Pole. So as a user facility, our data is freely available to any science users that will use it. We want everyone to use it. Specific to your question there, example of climate prediction would be lowering uncertainties related to aerosols and clouds. So ARM operates high-tech instrumentation such as radars, and they're going to tell us what type of cloud, where the cloud is. We also operate LiDARs, which are pulsing lasers, and looking at what returns off of them to tell us information about the aerosols and where they are. We combine that with water vapor information in the atmosphere, wind in the atmosphere to get this 3D picture. And we do this over time. So that 4-dimensional picture of what the atmosphere looks like. And so that's what we're providing to our science community. This is a very incredibly rich scientific quality data set that's available to all the scientists. We help the scientists use that data by providing products that combine the data sets, do calculations that many of them would be doing. We do that for them to take that additional step, which makes it more efficient. We help scientists use this data in models by running models, actually, different type of model that helps our observations get prepared to use in other models, or the output could be used to validate other models or in other analyses. Beyond that, for climate prediction, we need to understand processes that are on tiny timescales or decades long or longer timescales. To do this, we've operated for 29 years in our most extensively instrumented facility, which is, there's a picture behind me. This is in Oklahoma, Kansas. We've operated for 25 years in Alaska, for 8 years in the Azores, which is in the Atlantic. We also operate 3 mobile facilities for shorter periods of time, and we get pretty excited about these because we do move them often. We are currently in Colorado and we're in Texas, and in the coming years, we're going to go to Alabama and Southern California. So if you get back to the aerosol example, if you could imagine from Long Beach to San Diego, those tiny little aerosols, if you have a few of them, the sun's coming through. You get a lot more of them, they get trapped in there, you get that haze, you can see there's less coming through. Now, we might want to measure that on a different scale, but you can visually see that. You get a cloud in there, it's going to block more of that solar radiation. And so we're trying to support these models, looking at the energy balance and other things in those processes. So that's why we want to measure in those types of areas and what we want to do with that. One incredible thing about ARM and in the locations we go to, we don't just talk to the locals here and there. We actually engage with the locals. Local people are engaging by launching balloons for our facility. We hire local businesses to do site development, services that are there. And for our fixed sites that are there longer, it's actually local people who staff those facilities. So this is an economic support and engagement that we have with the local community. And in addition to that, the collaboration with them, it's not that we're just grateful and appreciative for what they do. It's truly valuable and critical to our success. They help us with the nuances of siting. They help us with understanding things that don't have a record. If a farmer is going to burn his field, he's not going to register that with anybody necessarily. So if the crop duster is in the air, things like that that are critical to our operation and the quality of our data sets. So we're very appreciative of that. Stakeholders that mentioned a couple of times here, and Kate's a stakeholder even beyond what maybe we would normally think, but there's stakeholders that need this accurate representation in models so that they can trust the output of how they're using the output from those models. This could be anything related to agricultural use, weather forecasting, think clean energy investments. People are looking at the opportunities and the risks associated with those. So we want all the information we're putting out there to be as accurate as possible. So however they're using it, they can truly trust what they're looking at. This can be also social impacts, things related to water availability and environmental justice. So we're really trying to make a big impact with immediate stakeholders and stakeholders beyond, the immediate ones for us. Part of your question was about rapidly enhancing the climate prediction. So I'm very excited to be a part and lead a DOE effort that's about artificial intelligence in Earth system predictability. So this is a multi-lab effort where we're looking at where can AI be most effectively used from the observations through to the models to enhance and accelerate the advancement of what we're doing in our research. So with that, in preparation for our workshop later in the year, we asked the science community to provide papers to tell us where they think artificial intelligence can enhance our system predictability. And we got a response of 155 plus papers with over 665 authors that are scientists and AI experts in the community. And they're from over 140 institutions. So clearly the community sees that there is value in the ability for this to accelerate advancements in modeling and the research that we're doing. One of those examples is in edge computing and instrument adaptation. So if you think about the instruments being on one end, providing the data through to the models and stakeholders at this end, that's the edge. So if we process the data right there at the edge, we can provide information to other instruments. And those instruments can adapt how they're sensing the atmosphere to better capture what we need to be looking for in that particular context. One manual example that you can think of is if you have a radar app on your phone and you see different colors at different times of what that radar presentation is. One is indicating that the radar is operating in clear air mode, the other in precipitation mode, so that it can better see the precipitation and clouds in that period of time. So that's one simple example. Additional efforts to accelerate advancement is collaboration. There was a NOAA DOE precipitation process and predictability workshop that a report just came out this month. This is a great effort that's interagency, and it's something for the AI for ESP community we're going to build on, because in that report, they've put key processes and uncertainties. They've identified those that need to be advanced on and worked on. So then we'll add in what could we do related to those and back and forth. And that's how we advance together, even though we're looking at somewhat separate missions at times. Additionally, ARM operates in a way that we provide or we work by FAIR data principles. This means our data is, so I usually use FAIR, findable, accessible, interoperable, and reusable. And ARM being a leader in the world in that, as it provided me an opportunity to serve as on a science advisory board for a European effort called Atmo Access. And this is a European effort that is organizing and looking to increase and improve the access to their atmospheric research infrastructure data. So it's the same things that we're working on here with NOAA and other things, and we're seeing that the other communities are wanting to do this as well. We're very excited. So with that, I think if we do these things, we use open source software, we leverage that in a way that can be used on the DOE extensive computing resources that we have. You're going to increase your data availability use. You're going to increase the data combination use that you're integrating those data sources. You're going to accelerate development of your model activity and contributions. And different agencies can work on different parts, but when you're sharing them back, you're moving forward faster in the group. So that's how I see, that's my vision.
Amazing. Amazing. Well, thank you for all of that information. I want to make sure we get to Kate too. I mean, Kate, we know the climate crisis is real. We know we got every metric is pointing to need for action, but it's really fair to ask where we even start and how we can make sure that we're deploying solutions that effectively protect all communities, and particularly the communities that are most immediately vulnerable to climate impacts. So you're a leader, Kate, in developing these multidisciplinary climate models for use by a variety of stakeholders. How can our current modeling capabilities guide efficient and equitable, really, climate action? What do they tell us about the work that we need to do to make sure that our most disadvantaged communities are going to benefit from clean energy investments?
Thank you, Secretary Granholm. So the models I develop are really focused on looking at different stressors, different systems, different scales, looking at the past, present, and future of all of these. And what we try to do, you think about it, the challenges that face an electric utility in the West are very different than the challenges that face an environmental manager on the East Coast. And so the kind of models we develop are trying to get at these different systems and different challenges. No model is perfect and we can't represent everything. So we're continually working to improve them. We also look at multiple different possible futures to better understand risks along potential pathways. One thing that we know, though, is that the climate is warming. And as you mentioned earlier, with increasing temperatures, it has consequences for people. We see increases in wildfire, flooding, droughts, crop yields, and all of these things impact our energy system, our agricultural system, water, and other things. And so we're continually working to improve these models and understand them. You asked specifically about different communities. And one of the things that you have to do if you want to understand how the system will affect different communities, we first have to represent those communities in our models. And that's something that the Department of Energy has been working on a lot, is trying to represent climate and people at finer scales. And so if you think back on climate modeling in the past, we used to think the best that a climate model could do was divide the world into these 50 kilometer by 50 kilometer grid cells. And you could just give you average climate in there, which isn't really that helpful for a local decision maker. And also at those scales, we don't really capture all of the processes that we know that are important. So some of the work that's been going on with the Department of Energy's Earth system model is to push to higher and higher resolutions. And at these resolutions, we can provide finer scale climate information. And we can also think about events that matter to people like hurricanes. So we can actually represent those in our models now. On the people side, economic models used to represent people as a single group. And we look at indicators like average income or GDP as drivers of change. But we know people aren't all alike and they don't all have the same income. And so some of the work that's happening at Department of Energy now is trying to represent different communities by dividing populations into different socioeconomic groups or different geographies. And we can then look at how those climate might impact those different people, and also how changes in things like the energy system might impact those different people. And this sort of information can be used by decision makers to think about policies related to energy equity or environmental justice.
Wow. I know you guys are delivering such amazing information, and we only have a couple of minutes left. And I know, Dr. Lubchenco, you had a question. Maybe Margaret can answer that, and we'll let that be our close.
So I'm just so impressed by all the great things each of you is saying. I'm sure each of you has seen some successes in your own programs that you would really like to see DOE and the Biden administration more broadly build out. So given that we're just going to target you, Margaret, what would you highlight as being in that category?
Thank you. I think in terms of DOE successes specifically, DOE is pioneering a new way of studying what ecosystems do when experiencing more disturbance. And they've started with projects in the Arctic and the tropics, and they bring together large teams of scientists from across the country and put those data into models to test our understanding. And we understand more about what's happening in Arctic permafrost and tropical forests. So we need those group projects. And then if I have 20 seconds more, I'll see if what gives me hope also is that we now know the US can reach this net zero CO2 emission goal, CO2 emissions from energy by mid-century. And I was part of a study recently that found this can be done very affordably. And there's multiple pathways to get there as long as we start now. So we know how to solve the problem and support good US jobs. And I think we could not have said that with technical certainty 10 years ago, but now we can.
Awesome. Margaret, way to come in just under the wire. Nikki and Kate, Dr. Lubchenco, thank you all, you great women. I love women scientists so much for joining us for this great discussion. Thanks to everybody for tuning in. If you're interested in learning more about our climate science work and all that we do at the Department of Energy, be sure to follow us on Facebook, on Twitter, Instagram, subscribe to our YouTube channel. We are all over the social media. Thanks so much, everybody. Have a wonderful afternoon.